Why does estimating population variance using this formula leads to a biased estimate, whereas this formula leads to an unbiased estimate? And what is Bessel's correction here? So we'll understand this in the next few minutes. So before this, first understand what is a population and sample. See, population is the entire groups that we are interested in, and sample is a subset of the population. Subset is basically a small part of something large. So some of the randomly selected subjects from the population is called a sample. Okay. Now, for example, the height of all the students, a data set containing height of all the students of a school is a population, and a data set containing height of 20 randomly selected students from the same school will be its sample. Okay. All the people of a country represents a population, and some of the randomly selected individuals from the same country is sample. Now, if we have the entire population, then why to consider a sample? So the reason is, in most of the real world cases, we do not have the data about the population, entire population. What we have is the sample. And to find some specific information about the population, we use the sample to roughly estimate this information. And in cases where we have the data about the population size is itself very large that it will be very difficult and time consuming to use this data to find the information about the population. So till now we understood that in most of the cases we use sample to estimate or guess the characteristics of a population. Now let's see where Bessel's correction is used. Okay, now listen very carefully. See, if we want to estimate the population variance using only the sample data, then Bessel's correction will come into the picture. Okay, now let's understand what is the population variance. Let's say we have a population and we want to estimate the population variance. Here we denote population variance as in terms of sigma square. So we're using sigma square to denote population variance. Okay, and let's say we are denoting xi to represent the population data points. Like xi is equals to x1, x2, x3 dot 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 xn, where each of these x1, x2, x3 are individual data points of the population. N denotes the population size, that is number of data points in the population, and mu denotes the true mean, that is the population mean, which is basically the average of the population data points. Okay, now let's assume we know each of the population data points, and it is also not very big enough so as to cause difficulty in our calculation. Then in such a case, we will calculate population variance using this formula, the OG formula to find the variance. Okay, this is the original formula to find the variance. Cool. Now let's say we draw a sample from the population, from the same population, and we want to find the sample variance. Here we are denoting the sample s square as the sample variance. Okay, here small xi denotes the sample data points like x1, x2, x3, where each of these x1, x2, x3 are individual sample points. N denotes the sample size, number of data points in the sample, and x bar denotes the sample mean, which is the basically the average of sample data points. So the sample variance is calculated by the sample variance formula. This is the variance formula. Okay, cool. But as we have discussed, in most of the real world cases, we don't have all the population data points. Okay, we don't know the true mean, and we also don't know the population size. Now, in this case, in this situation, if we want to calculate this population variance, then we can't calculate its exact value because the population is not available. So what we will do, we will guess or estimate the population variance using the sample. So we have the sample, then we will estimate the population variance using the sample variance formula. So we will find the sample variance and we will assume that yes, this sample variance can be used to represent the population variance. Okay, cool. But here, population variance represents the spread of the population, whereas sample variance represents the spread of the sample. And if we use this to estimate the population variance, then the estimate will be biased downward. Cool. Now, to get a feel of why the spread of the sample is different from that of the population, let us consider an example. Let us assume uh, the height of all the students of a school is distributed on a number scale like this, uh, where each of these black dots represents where each of these black dots represents the individual height values. So let's say that so here around four students are there which are having height closer to 100. So this is what it is meant by this. This basically you can assume this as a dot plot. Okay, where each of these black circle represents the individual height values of the students. Okay, now let's randomly draw a sample. So the red dot represents the sample data points. So you can see the spread of the sample is this much, whereas the spread of the population is this much. So we can clearly see that there is a difference between the spread of the sample and the spread of the population. Okay, so due to this difference, if we use the sample variance as an approximate value for population variance, then it will introduce a downward bias. And to remove this biasness, we will include Bessel's correction. Okay, so what is Bessel's correction? See, in the denominator, in place of n, we will simply add n minus 1. And this n minus 1 is the Bessel's correction. Now, we have two questions before us. Why estimating population variance using the sample variance formula will be biased downward? And why adding n minus, why adding n minus 1 instead of n in the denominator will make this estimate unbiased? So, before this, first understand what is meant by biased. See, if you find an estimate by following a procedure, now by following a procedure, now if you repeat this procedure so many times, let's say 10,000 times, to find 10,000 different estimates. Okay, and if you average all these estimates like this, and you find out that the average of these estimates, these 10,000 estimates, is not is equal to the real value for which we are estimating, then the estimate and the procedure will be called as biased. Okay, and if the average of the estimate is less than the real value, then we will say it is biased downward, and if the average of the estimate is greater than the real value, then we will say it is biased upward. Okay, now what was our procedure? We have the sample, we found the sample variance, and we have estimated this, we have approximated this as our population variance, we have taken this as our population variance. Okay, now in real world a lot of bias can come while during any procedure. Okay, but here Bessel's correction particularly deals with the downward bias that will come due to using the sample mean. So the downward bias is basically coming due to using the sample mean. Okay, so let's look at how the sample mean introduces bias in the estimate. So for this, let's consider a numerical data set. You find its mean. Now we will find the sum of squared deviations. Now what is this term? See, deviations is basically deviation from the mean is basically the distance of the data point from the mean. For example, deviation of 10 from 30 is 10 minus 30 is minus 20. Okay, so deviation is basically the distance of each of the data point from the mean. Now square deviation, you simply square the deviation. So this is what you will get. So now let's find the deviation of each of the data point from the mean, and let's and also the squared deviations of each of the data point from the mean, and let's put it in a table. So like this, here yi column represents the data points, and the second column yi minus m represents the deviations, and the third column yi minus m square represents the squared deviations. Now you find the sum of this column, the squared deviations column, and what you will get will be the sum of squared deviations of this data set from the mean. Okay, now listen very carefully. For any numerical dataset, the mean is the unique value from which the sum of squared deviations is minimum. Now, what do I mean by this? Instead of mean, you find the deviations of each of the data point from any value. You take any value and find the deviations of each of the data point, and then you find the squared deviations of each of the data point from the same value, and then you will find and then you find the sum of squared deviations. So the final value that you will get will always be greater than the sum of squared deviations from the mean. Now, what do I mean by this? So let's understand. It once again. See, okay, look, what we did. What we did in some finding sum of squared deviations from the mean. We found the distance of each of the data point from the mean. Okay, then we find the squared deviations of each of the data point from the mean, and then we calculated the sum of the squared deviations from the mean of each of the data point, and what the final value that we got is the sum of squared deviations is this, the sum of squared deviations from the mean. Now, in place of mean, you put any value. Let's say you put 10, and you find the deviations of each of the data point from 10. Then you find the square deviations of each of the data point from 10, and then you sum the squared deviations column. The final value that which you will get will be the sum of squared deviations of the data set from 10. So the final value that you will got will always be greater than the mean. Or in place of 10, you take 20 and find the sum of squared deviations from 20. Or even any point apart from this data set, you will always land with a sum of squared deviations greater than the sum of squared deviations from the mean. You can do this experiment yourself. Instead of mean, you take any numerical data set, and instead you find the sum of square deviations from the mean. Then instead, in place of mean, you take any value, you take any number, and then you find the sum of square deviations of the data set from that number. You will always land with a value which will be greater than the sum of square deviations from the mean. That is, the sum of square deviations from the mean will always be minimum, and this is a fact. You can check it yourself. Okay, so till now we know that the sum of square deviations from the mean will be minimum for any numerical data set. So keeping this aside, what we were discussing, population variance estimate with this formula will be biased downward. Now look closely at the numerator in right hand side. Here xi is the individual data points of the sample, and x bar is the sample mean. So this is the sum of the square deviations of the sample data set from its mean, correct? And because this is from the mean, this term will be minimum in comparison to any other value placed in place of x bar, that is the sample mean. Okay, understand this clearly. See, in place of this x bar, if we put any value, then this entire value will be greater than this value that we got using the sample mean, right? So due to this property, sum of square deviations from the mean is minimum. This procedure or formula that we are using will introduce an effect, and this effect will pull the estimate. What is our estimate? Our estimate is population variance. We have estimated population variance using this formula. So due to uh, this effect will pull the our estimate towards the minimum side, and this effect is the downward bias. Okay, so let's understand what this downward bias will do. Suppose we have a population, okay, from which we have taken so many samples. Let's say we have taken 1000 sample, where each of these S1, S2, S3 represents a unique sample. Okay, and for each sample, we estimated population variance using this formula, this biased formula. Okay, the sample variance formula. And let's say S1 square is the population variance estimate from the sample S1 using the sample variance formula, that is the biased formula, and S2 square is for sample 2, and so on. Okay, cool. Now if we average all these 1000 estimates, then it will be less than sigma square. Why? Because of using sample mean in the formula. Now listen very carefully. It does not mean that each of the 1,000 estimate of sigma population variance will be less than the real population variance. Some can be less than the real population variance, but some can also be greater than the real population variance. But due to the downward bias, if we average them all, if we take the average of the estimate, then it will always be less than the real population variance. So to counteract this decreasing bias introduced by using sample mean, Bessel's correction is used, which will increase the final value of each of the estimate and it will make it unbiased. Okay, so what is Bessel's correction doing here? See, Bessel's correction is simply increasing the denominator by 1, okay, which will increase this overall value by a little bit, and this will counteract the decreasing bias that will come due to using sample mean. Cool. Now there's a special case. We have the sample from the population, but in this case we also have one extra information. We also know the population mean. Okay, now in this case, when we want to estimate the population variance using the sample, we will use population mean or true mean in place of the sample mean. Yes, and in this case we are not required to include Bessel's correction, because Bessel's correction is used to counteract the decreasing bias introduced due to using sample mean. But here we are using population mean, that is true mean, and true mean is a fixed value apart from the sample. Okay, so it will not add any decreasing bias to our estimate. Cool. So for more clarity, let's take an example. Let's take an example of this numerical data set. Let's say this is our population. Now let's calculate the population variance using the using the OG formula, the real population variance, and the real population variance comes out to be 825. Okay, and the population mean is 55. The population mean or the true mean is basically the average of the population data point. Okay, now let's take it. Now let's take a sample from this population. So this is our sample, and the sample mean that we got is 52.5. Okay, and this is our two estimates. The first one is the biased one, as we have used sample mean. Okay, and the second one is the special case that we have discussed just now, where we use the sample as well as the true mean to estimate the sample variance. Now let's put these in a table. Cool. And we'll take another sample and find the same for this sample. So in total, I'm taking 8 samples and finding these two estimates in each sample. See, the calculations are really simple. That is why I'm not showing it here. You just plug in the values and find this estimate. So this is our 8 samples. And if you want, you can calculate these estimates yourself. Okay. Now we'll find the average of both these estimates. Okay. See, average of the estimate is simply the average of both the column. Sum all the values of the column and divide by the total number, that is 8. Okay, now I also found the population variance estimate for these same 8 samples using the Bessel's correction formula. So I will just plug in the estimate here. So yeah, now just look at this biased estimate column. As we discussed, due to using sample mean in the estimate, it will be minimum. The estimate will be minimum or towards the minimum side. But we have also discussed that this doesn't mean that each of the estimate that we will get using this biased procedure will be less than the true population variance. Some can also be greater than the true population variance. Like here, you can see 1050. This is greater than the real population variance. due to sampling variability. Okay, now look at the average of the estimate using Bessel's correction and the average of the estimate with true mean in place of sample mean. Okay, and compare these two values with the true population variance. Okay, so you can see these two are more closer to the true population variance in comparison with the average of the estimate that we got using the downward biased formula. Okay, so hope so whatever we have discussed till now is clear, and if you have any doubt you can leave a comment and we will meet in the next video. So yeah, thank you.